Alright, so let's have a look at another question from the topic of ordinary differential equations. So now we're going to have a look at a specific solution using our series methodology. So the equation in question, the direction for this equation just says solve. We are told the equation is y prime minus x squared y is equal to 0. And we are told here to use y of x is equal to the sum from n equals 0 to infinity a n x to the n. So first we need to take a derivative. So y prime of x is going to be the sum from n equals 1 to infinity of n times a n times x to the n minus 1. And now we're going to plug these both in. So this tells us that y prime minus x squared y equals 0 becomes, well, we'll plug in our y prime from down here. So this is the sum from n equals 1 to infinity n a n x n minus 1 minus x squared times y, which is this, times the sum from n equals 0 to infinity a n x to the n. This is equal to 0. So we can put this x squared power into this xn. So this will give us the sum from n equals 1 to infinity n times an times x to the n minus 1 minus the sum from n equals 0 up to infinity an times x to the n plus 2 is equal to 0. Now ideally we want both of these powers to be the same. We could just make them the same by turning one of them into a different power. I'm actually going to transform both of them so they're xn. You don't have to do this. I'm going to do this because I like this. I like the process of turning these into xn's. So this is the first one. We'll call this number 1. This is the second one. We'll call this number 2. We'll do these over on this side of the screen so that this stays, so we can keep our working on the right side relatively neat. So we have the sum from n equals 1 or 0, it doesn't actually matter, we'll just call it n equals 1, up to infinity times n times an x to the n minus 1, and we are going to let n equal k plus 1. So when we replace the n in the power, it becomes k plus 1 minus 1 is k. So this gives us the sum from k plus 1 equals 1, well that implies k equals 0 up to infinity, times k plus 1 times a subscript k plus 1 times x to the k, and then we are going to let k equal n. So this gives us the sum from n equals 0 to infinity of n plus 1 times a subscript n plus 1 times x to the n. And this becomes our substitution for the first summation. So summation from n equals 0 to infinity n plus 1 times a subscript n plus 1 times x to the n. Now we need to do our second one, which we'll do over here. So we have the sum from n equals 0 up to infinity an times x to the n plus 2. So here we need to let n equal k minus 2 to cancel the plus 2 in the power. So this gives us the sum from k minus 2 equals 0, well that implies k equals 2 up to infinity times a to the k minus 2 times x to the k, and then we're going to let k become n. This will give us the sum from k equals 2 to infinity times a, this is now n's, we're swapping k's for n's, n equals 2 a n minus 2 times x to the n. So minus the sum from n equals 2 up to infinity a subscript n minus 2 times x to the n. This is equal to 0. So now we can factor the x to the n out. So we are going to get x to the n times the sums start at different points. We can't just make them start at the same point, so we'll just leave them for the time being. Sum of n equals 0 up to infinity times n plus 1 times a subscript n plus 1 minus the sum n equals 2 up to infinity times a n minus 2. This is equal to 0. Either x to the n is 0 or the thing in the brackets is 0, so we're going to let the thing in the brackets be 0. So this implies that the sum from n equals 0 up to infinity times n plus 1 times a subscript n plus 1 minus the sum from n equals 2 to infinity a subscript n minus 2 is equal to 0. Now we're going to start plugging in n's. So we are going to let n equal 0. When n is 0, this second term doesn't count because it doesn't start till 2. So the first term gives us 0 plus 1, that's 1. So we get a to the 1 is equal to 0 when n is 0. Now we are going to let n equal 1. Now, because we don't have an a1, because we don't have an a0, we'll define a0. We'll say a0 is a0, and we'll say a1 is 0, because we've just found this. When n is 1, we're now going to get 2a2, second term still doesn't count, is equal to 0. So this implies a2 is equal to 0. So we've got a0 is a0, a1 is 0, a2 is 0. Then we are going to let n equal 2. Now this second part will start to count as well. So we get 2 plus 1, that's 3a3. So we get 3a3 minus, we've got n is 2, 2 minus 2, that's a0. So minus a0 is equal to 0. So this implies if we add a0 to both sides, divide both sides by 3, tells us a3 is equal to a0 divided by 3. And then if we let n equal 3, we are going to get 3 plus 1, that's 4. So we have 4a4. And then we're going to have, this will become, if n is 3, 3 minus 1 is 1, that'll be a1. So minus a1 equals 0. This implies a4 is a1 divided by 4, but this is 0. So we have an a0 term, we have a1 is 0, we have a2 ends up being 0, and then we have an a3 term, which is a function of a0. So let's do a few more of these because we're not getting much out of this. So sometimes you'll get terms straight away and it will become obvious whatever series you're after. Sometimes you will not get terms straight away and it will be much more complicated. So we want another term. N is 4, we'll get 4 plus 1, so this will be 5 a subscript 5 minus a subscript, this will be 4 minus 2, which is 2. This will be equal to 0. So this will tell us that a5 is equal to a2 on 5, but we know a2 is 0, so this goes away. So then we're going to let n equal 5. This gives us 6a6 minus 5 minus 2 is 3 minus a3 is equal to 0. This implies that a6 is equal to a3 divided by 6, but we know a3 is a0 on 3, so this is actually a0 on 18. So now we're starting to get a sufficient number of terms to actually help us identify what we're after. This one is a little bit tricky to identify, but it can be done. So we have, this implies that our solution, which is of the form y of x, ends up being equal to a0 plus a1 times x to the n, but a1 is 0, so there's no a1, plus a2 times x squared, well a0 is 2, plus a3, which we know is a0 on 3, so this straight away can become a0 on 3 times x cubed, plus a4, that's 0, a5, that's 0, a6 is a0 on 18, a0 on 18 times x to the 6, and so on. Now a0 is the only term that we have here, the only loose term, so this suggests this is going to be one solution. It's going to be a0 times 1 plus x cubed on 3 plus x to the 6 on 18 plus dot dot dot. Now our task is to work out what that series actually is. And this series here, as it turns out, you can identify this by a computer. You can use a whole bunch of Taylor expansions if you want. This ends up as e to the power of x cubed on 3. X cubed on 3. And so therefore, y of x is equal to a naught, some constant, multiplied by e to the x cubed on 3. And this is the solution that we're after here. And this is, again, to find this solution, once you get these series, you'll look up lists of known Taylor polynomials. You can construct Taylor polynomials for certain expressions. This is a slightly unusual Taylor polynomial, but it does work. Now, in this case, we are actually able to test this solution. So we want to test this solution to confirm. We want to check. So we need the function. The function y is some constant a0 times e to the x cubed on 3. The derivative, y prime, is going to be a0 times the derivative of this, which will be e to the x cubed on 3, multiplied by the derivative of the power. That will be 3x squared on 3, that will be x squared, so times x squared. So then we're going to plug this in. We get y prime minus x squared times y is equal to 0. This becomes a0 times x squared times e to the x cubed on 3 minus x squared times a0 times e to the x cubed on 3. Now these are the same. Their difference should equal 0. This tells us 0 is equal to 0. This is true. So our manual check, which was not particularly difficult in this case, confirms for us that a solution to this particular problem is y of x is equal to a0 times e to the power of x cubed on 3, and we were able to solve this using series solutions.